put a link up here. It's called All About Protective Relays, and it's by a company, LS Electric. And so this is actually a great document with a great overview. Couple of headers, gives you a description of what a protective relay, and it says power interruptions drain an estimated $150 billion annually from the U.S. economy. And most of these start with a fault that lasts less than a second. And in that brief moment, equipment can fail, production can halt, safety can be compromised. The shocking thing is that most of these incidents could be avoided with faster fault detection and isolation. And that's where protective relays come in. They have basically 4 stages. Fault detection. They identify abnormal operating conditions instantly before significant damage occurs. This is done by connecting it to CTs and PTs and measures voltage, measures current. Trip initiation sends a precise command to trip circuit breakers for fault isolation. Fault duration reduction, so it minimizes the time the fault is there. And also the newer ones are system monitoring. They can record and analyze and send data off to central areas. How do they work? Well, a protective relay comes in many sizes and shapes. It's a pretty generic name. So they monitor something. They monitor current using CTs. They monitor the voltage using PTs. They can monitor the frequency by looking at the exact frequency, 60 hertz. And then they have thresholds that they would acknowledge and look at. This has exceeded some threshold. So the current's too high, the voltage is too low, there's a voltage dropout or a voltage spike. And then the logic then finds out that this is now an abnormal situation. It's exceeded the thresholds that have been set, exceeded the limits, and therefore it signals a trip action on its output, and that would open a breaker. Then the other thing is the intelligent ones, the new ones that are solid state, they can, all of them will reset themselves after they trip in case it reoccurs, so that they don't have to be manually reset. But also the reporting thing is they then have to indicate to some central source what happened. This could be done through flags, so that an operator walks past a mechanical protective relay and he sees a big red flag set, knowing that that's the one that tripped. Or in the case of the newer ones, they can actually send email or send data to a central area. So they're monitoring. The relay measures voltage, current, frequency, anything else using current transformers, CTs, and VTs. Those 2 transformers, as you know from PT and D1, knowing the voltage and the current, you can get the power factor, the watts, the VARs, the VAs, everything. It then compares, and fault detection compares these measurements with predefined thresholds or limits. And if they blow past a limit, the relay instantly flags the event as an abnormal condition. Once the condition is detected, the relay's logic system decides whether isolation is necessary. It factors in fault severity, type, location, because you don't want an unnecessary trip shutting down a huge area. It will then generate a tripping signal. So there's usually a circuit breaker involved. This relay will then send the signal to the circuit breaker, which trips and opens the network. After the fault's cleared, the relay logs all the event details for analysis, and it may automatically reset, or they can be set to automatically reset or have to be manually reset. Now, many different types. The older ones, and one of the ones you'll be working with in Lab 11, is an electromechanical one. They don't take any power, they just work, and they will trip, and you can set the tripping for instantaneous or for a timed trip, which is like an overload. You can have numerical relays, Distance relays, they'll monitor the impedance of a line, and if it drops too low, they know that there's a fault to ground. Differential, you can check the current or the voltage on the upstream side of a relay and the downstream side. And if there's a difference, meaning that something on the secondary side shorted out and the voltage is lower, it'll trip. And of course, the overcurrent trip as well. Older electromechanical ones, they use magnetic induction, and they'll spin a wheel, and if the wheel spins long enough, it hits a current trip device, the contacts close, and its output will send a trip signal. Static relays, they're another name for solid state relays. Electronic, no physical mechanical parts, no springs. They are just a little easier. No moving parts means less maintenance, less prone to environmental damage from vibration or dust or dirt. Solid state stuff is pretty durable. It is subject, of course, to electrical spikes if it goes through from the power supply side. They do require a separate power source to run. It's like a computer, it has to be plugged in, or a PLC. So they're a low-end PLC, single function. Uses analog inputs to measure current or voltage, and then you write a program to set a trip point, and it will then trip. Numerical, these are advanced relays or microprocessor based. Static relays, it's like an analog value. You have amplifiers in there, and you can set the gain and set trip levels, and it will trip. Numerical is digital. It's a PLC, basically, a very precise function. They can do all kinds of things. They can analyze system parameters using digital algorithms. They can record data like a data recorder, self-diagnostics, communicate with SCADA, HMIs, other supervisory systems. So it is a full, powerful machine. And they now even can be set up for different protection zones. Distance relays detects faults by measuring the impedance between the relay location and a fault point. Basically, it measures the impedance across a line, and they know what the impedance is between substation A and substation B. If the impedance changes, they know there's a short or a fault to ground. And when the measured impedance falls below a preset value, the relay assumes the fault lies within its protection zone and trips. On a long run for something like Thunder Bay to Manitoba, if there was a fault, given the current and the amount of current flowing with the voltage, they can calculate the impedance, and knowing the impedance per kilometer, they could roughly estimate how far along, say, a 500-kilometer line, how far along that line the fault actually occurred. And it gives them a good starting point to go look for problems. And again, differential relays, comparing the current entering and leaving a specific zone. So if it isn't the same, then there's a problem. So what are these used for? Just about everything. Transmission protection lines, transformer protection, motor generator safety, bus bars, feeders, industrial automation systems. And the advantages of some of these newer ones, and you're going to get a whole course on these, in protection and control, is the intelligence. You program everything. They have all their inputs, they have all their outputs. As I say, it's very much similar to a specialized PLC. They have event recording, data logging, and then from a distance, everything is Ethernet. These can be in a remote location, and from a control room, you could reach out and upload all of the data from that device. Any kind of tripping information, you could monitor the currents, see the highs and the lows. And so it just gives you much, much better control. And then you can fine tune the tripping points of all these devices. The last thing you want is your main substation or main power supply tripping and shutting everybody down. You want the localized protective relays that are the closest to the fault to be the fastest ones and the first ones to trip, so that everybody else still has power. So this is a good document. Note periodic calibration is in there. That's really important. These things have to be tested. There are crews that just go around and calibrate all of these. That is exactly what you are doing when you're doing Lab 11. Theoretically, you're going to put in known currents and test the trip time and compare it to a graph and say, does it pass or fail? We don't get quite that detailed, but that is the main idea. Correct coordination. Trip settings should be planned to ensure each device operates in the right sequence. In other words, you want to isolate faults closest to the fault, not an entire area. So what do we get when you're doing Lab 11? Pickup current is basically the tripping point. That is 100% full load current. You set it. Now you can set it in a variety of ways for your system. Every system is going to have a different setting. So once your current goes above the pickup current, it's in the fault zone. Then your timed contacts will start to count. And the higher it goes, hopefully the current will go back down again, and then it never actually trips. But if the current goes really high, then the instantaneous trip will go. They have settings like the delay. That's how fast it is before it actually trips. And this is how you'd coordinate with other ones. So the slowest ones are going to be at the substation. The fastest ones are going to be out in the field closer to the fault. Reset time, how long before it resets again. And then the sensitivity. High sensitivity can catch early stage faults before escalation, but in a system with frequent load changes, this is balanced because you'll get false tripping. So, protective relays. Very simple device really, but they're getting much more powerful all the time.